Python is also an object-oriented language. We're going to talk more about this in the next module in the future. But for now, what's useful to know is that all data and data types in Python are objects. And objects can be thought of as a literal thing, a literal noun, right? That exists and that has state and behavior, okay? And we can continue thinking about this in terms of parts of speech. State defines the attributes of an object. The state are the adjectives. Behavior are what an object can do. Those are your verbs. So, for example, int and float and string are all built-in data types. These are all classes in Python that you can create objects from. Int has state. It can hold a number. Float has state. It can hold a decimal number. String has state. It can hold a string of characters. A list can hold multiple different objects. So an int with a value of 3 is different than an int with a value of 5. They have different state. Behaviors are the methods that can be called. So our string type, you can call .strip, which will take off white space on the edge. Our list, you can call .append, and you can add a value to the end of your list. Okay, so objects are the data and data types that are held in Python. State are the value that are held in the object, and behavior are the methods that you can call on each of these objects. So let's get a little lower, right? Let's get into the code. How do we store data in Python? Okay. And this is in a format you're going to see a lot in this class. You'll see this more when you get up to 325, which I believe is called Paradigms of Programming Languages. But this is going to be EBNF, which stands for Extended Backus-Naur Form. The idea being anything in these angle brackets are not literal. They represent the fact that this thing can be replaced by something. In this case, some value, any value. So anything that evaluates this to a value can be put there, right? A function call can be put there. A method call that returns something can be put there. A literal can be put there, such as this, right? An equation can be put there. All of those are going to evaluate to some value. And what ends up happening is the value gets assigned into whatever this variable is, this identifier, right? So in this case, our identifier is num courses. But how does this work behind the scenes? Well, behind the scenes, the interpreter says, okay, I want to create a block of memory, and then I'm going to associate the identifier num courses with that block of memory. And then whenever the user puts in num courses, I know that it is this block of memory that I need to use, and we can access or change, or we can invoke methods off of that identifier by using num courses. And we can see this in action if I pull up the Python interpreter. We can see this in action when we declare, you know, x equals 5, right? Okay, fine. X, it's 5. But look what happens when I do this. When I print out the hex of the ID of this variable, okay? This here is the hexadecimal representation of the memory address. That's what that is. This is the memory address for this variable. So anytime we put in X, the interpreter says, oh, I know what that is. Let me look that up. Let me go to the lookup table and find the memory address, and then I can go and do what I need to. In the same way that when you put in a URL in your web browser, right, the DNS, the domain name service, looks up, hey, that thing, I know what that is. That's this IP address. And it routes you to the proper computer. Same concept, right? This is so that we can code using names, these abstract ideas, rather than simply going, oh, at this memory address, store that. So we've talked about objects and we've talked about data, but I've also used this term type a couple of times. Okay. What is type? Type is the kind of object, such as an int or a float or a string. Okay. We're also going to hear this. We're going to hear the term class in the next module. Type and class are associated. Okay. In a future module, we're going to talk about the distinction between type and class. But for right now, type and class are going to be, don't worry about the difference, because for our purposes, those are going to be the same thing. But what's important to remember is that Python is dynamically typed, which means that variables do not have to be declared as a type. I don't have to say int x equals 5, right? Like I do in Java. I can just say x equals 5. And Python will say, that's great, I love it. If you said int x equals 5 in Java and then said x equals the string of 5, Java would freak out. Java would say, we cannot do that. That's not allowed. I must contain a number. I can't contain a string. Okay. So this is nice for us. We can change variable type just depending on the value assigned, right? And 5 has a type. This number 5, right? However you describe it. What type? What is that data? Well, it's an int. Okay. What is this? Well, it's a string. Okay. And we'll see how type and objects and classes all relate in a future module. But now we need to create objects. We need to figure out how we create objects in our code. Right? This is called instantiation, is the fancy word for it. But it just means creating an instance of an object, right? Instances, and we're going to get into these definitions in the future too. Instances are individual objects. And we can go about this two ways. We can say, I'm going to do this explicitly. I'm going to call the constructor. And a constructor is a special method that has the name of the object or class type. Okay. It looks like this, right? This is the ints constructor. And the constructor returns a reference to the newly created object. So constructors have the same name as the data type, parenthesis, arguments. It takes an argument list, right? It doesn't have to. It could have no arguments and be the default constructor, or it could have one or more arguments, and then a parenthesis to close off the list. And this will go in and it will call a specific method, and we'll see how that works in the future. It will call a specific method inside the int class, and then when it's done, it will return a reference to memory where that object has been created, and it will put that reference in X. And now X contains the memory address for this object. We can also use a literal form. That's where we use a literal value for defining the object. And this is used with common data types that have been predefined in Python, right? This is the most common form that you will see of creating an object. And we've seen this already, right? We see this in here. Pointer options, erase all, and slide, right? So yeah, we have a literal here and a literal here. We also have a literal here. We're saying, hey, I want you to create a dictionary, right? These symbols say set, these symbols say dictionary, with these exact literal values inside. No more, no less, nothing different, right? This is the literal form of creating a dictionary in Python. So you're going to see this way more than you're going to see the constructor form. Now we're going to talk about methods. Methods, like I said, they're the verbs. They're the behaviors. They're the actions an object can take. And methods inherently are based on the state of an object. So they require the referencing name of the object, right? These use the dot operator. You can say that a method is invoked or called. And it is done by using the dot operator, right? And the dot operator is used in many circumstances, but always represents a sub-aspect, right? We can put a dot operator behind a module and get a specific class, or we can call a class and put a dot operator. We can call an object and put a dot operator and get a specific method, right? Dot operator always drills down. The thing on the left is more generic, the thing on the right is more specific. So for instance, we could say dot append, and that will add an exclamation point at the end of the string. Technically, this I believe will return the data, right? Because string is immutable. Okay. But the key thing is append. Append takes something and puts it on the end of something else, right? We need the data in data. We need this string. If we don't, the behavior is not fully defined, right? X equals 1, 2, 3. Y equals 5, 6, potato. X dot append 9, right? And this will put 9 on the end of X. But notice that it takes into account the previous information, the state of the list. And then it does what it is going to do, right? Append adds something to the end of the list. Great. Well, I need to know the state of the list. I might be provided with additional information through an argument. If you have a method that doesn't take into account the state of the variable, that's not a method. That's a function, right? The mathematical concept of a function is that it takes information from one set and maps it onto another set, right? It is information mapping. It does not need any additional information. We have our function f of x, and it's 3x plus 2. If I put 1 in, I get 5. If I put 2 in, I get 8. If I put 0 in, I get 2. No additional information is needed, only the input. and the function definition. With a method, yes, you have input. Yes, you have a function definition, but you also have the state of the calling variable. Now, different objects can have different methods. Different objects can have the same methods. Different objects can have different methods with the same name that do different things. Just because I create an object with append doesn't mean it's going to do this. It might do something totally different. This is why naming is so important. You want to give your variables, your functions, your methods, good names that describe what they do. Okay? If there is an established concept like append that is used other places in the language, you probably want to avoid using this name to describe something unless it does the same thing. There's nothing that prevents you from doing it, but it's confusing. So this is why naming conventions are so useful.